Okay. Hello everyone, we are from Group 1 and today we will be teaching you about advanced packaging interconnection. Okay, my name is Lee Keng Ek and I'm joined with my teammates which is Lo Yong Wei, Yu Ying Jie and Laila Osman, with Amna Yasser. So for the decades, the industry relies on shrinking transition, but today fitting everything onto one massive chip is too expensive and create huge thermal issues. Packaging is not longer just a plastic shell, so it is what determines the device speed. That's why we introduce advanced packaging. Yes. Next. Okay, now we shift into our type of technology. Yes, okay, this shift driven by three main needed for the advanced packaging. First, speed. AI and advanced computing need faster data flow and shorter the signal path. Second, yield. Okay, making one giant chip leads to high defect rates. Breaking it down into smaller pieces lowers the cost. Thirdly, is the heterogeneous integration, where this is we now need to mix logic, memory, sensor, which are all made on entirely different process nodes into one package. This is why introduce advanced packaging. So to understand this, we will be looking in the physical signal pathway. Okay, the signal leaves the bare silicon die and travels through the first level interconnect to the packet substrate, and finally to printed circuit board. Next, the first level interconnect is our focus today. If it is too long, you lose the speed, right? If it is too short, you gain. If it is short, you will gain the performance. It will. I will now pass it to Yinjie to explain our first technology, which is wire bonding. Thank you.
Thank you, Ike. Wire bonding is the oldest and the most widely used method. Imagine a very-thin metal wire, usually gold, copper, or silver, acting as a bridge between the bond pipe on the die and the substrate. The machine melts the wire tip into a ball, presses it onto the die, loops the wire through the iron, and stitches it to the substrate. The biggest advantage here is the cost and maturity. It's cheap, easy to inspect, and perfect for the low to medium input-output devices like the simple sensors. However, it has serious limitations for modern tech because the wires are physically long, secrete parasitic inductance, meaning the high-frequency signals degrade. Furthermore, the copper wires can suffer from corrosion in acidic environments. Because of these speed limits, the industry developed the flip chip technology, which my friend will continue explain.
Okay, thank you, Inje. The fish feed is literally freeze the script. So instead of pressing the die face out using the long wire, we press the solder bumps and the cola pinners directly on the edge surface of the dies. So we then freeze the die upside down and mute those bumps directly on the substrate. So we will how to do it? We will fill the gap and with explosive underfill to protect the joints. So you can now see the features to see what with the fishery technology. So this teaches us an important rule of the packagings. Also, the path equal better. So because of the bumps are teeny, we are get the excellent high frequency speed and massive input and output density. So this is standard for CPU and the GPUs. But for the trade-off is reliability. So the silicon dies and the substrate expand at a different lag when they get hot. So this thermal mismatch cause the package wear patch and can crack the solder joint over the time. So to solve the issue of the making giants hot fish screen, we can use another technique which called the crimping technology. So the crimping technology, uh, our next group member will share with you. So thank you.
Thank you, Yong Wei. Now we have chiplet technology, the future of advanced packaging. So instead of manufacturing massive system on chip, we split the system into smaller functional blocks called chiplets. For example, one for CPU, one for memory, and one for I/O. Then we package them together so they act as a single brain. These chiplets communicate using incredibly dense die-to-die interconnections such as silicon interposer or hybrid bonding. The main advantage is that smaller dies have a much higher manufacturing yield, and you can also mix match technology using 5 nanometer process for CPU and a cheaper 14 nanometer process for the I/O. The main challenges are thermal management since we have multiple hot dies packed tightly together, and the need for standardized communication such as UCIe standard. Now Leila will summarize the trade-offs and our scientific literature.
To quickly compare, wire bonding is the winner for lowest cost but the loser for speed. Flip chip provides the high speed and density needed for modern computing but introduces thermal stress. Chiplets provide the absolute best performance and yield for AI and data centers but carry the highest initial design cost and complexity. We analyzed 5 recent papers to understand the current research trends. We focus on the specific problems they solve. First, Law 2022 addresses the problem that SoC scaling is becoming too expensive. The proposed solution is shifting to 2.5D and 3D integration to bypass more slow limits. And second, Law 2021 highlighted the problem of integrating diverse functions on one chip. The solution is chiplet integration to allow modular design reuse. And third, Ross et al. Investigated the problem of copper wire bond failures. They identify hydrogen evolution and chloride as the triggers, proposing stricter environmental controls. Fourth, Lim et al. Tackled the problem of flip chip warpage and thermal stress. Their solution used finite element analysis to mathematically optimize the underfill thickness before manufacturing. And finally, Zhou et al. Identified that traditional solder bumps are too large for 3D chiplets. Their proposed solution is copper-to-copper hybrid bonding, allowing direct metal bonding for ultra-fine pitch.
Hi, I'm back. So to conclude, packaging is not longer just protection. It is a performance driver of the post-Moore era. As we move forward, the industry is transitioning from long wire loops to short solder bumps, right? And eventually to ultra-fine hybrid bonding of chiplet. Mastering this interconnection is the key to unlocking the next generation of computing. And we need to have this kind of what technology in order for us to improve our needs and what the society is developing. So we now thank you for listening to our presentation and have a nice day. Thank you.